Thank you very much, Venkat. And first, want to welcome you all to this training session. And I want to first introduce the other people who will be speaking with me. In fact, since you can see them, I'll have them introduce themselves. I'm Bill Bain. I'm the founder and CEO of ScaleOut Software, and I'm going to give you a technology overview. Oleg?
My name is Oleg Shmytov. I'm engineer manager at ScaleOut Software. I'll be talking about how to use .NET library to build the real-time digital twins.
Brandon?
My name is Brandon Ripley. I'm one of the engineers here at ScaleOut, and today I'll be talking about assessing threats for the power grid and also describing how to build a digital twin model in Java.
Thank you. And Olivier?
Hi, my name is Olivier. I joined ScaleOut Software this year. I'm part of the engineering team, and today I'll be talking about an example of a digital twin application with contact tracing.
Okay, thank you all. So I hope you can see the screen, and I'll get started. Let me first point out that the documentation for the real-time digital twin software APIs can be found on our website. There's also a user guide. Also, these slides, and the demos that you'll see, the code for the demos will be on GitHub. We created a GitHub called Digital Twin Demos, and this is the link to it. And I think everything is posted now, so you can feel free to go to GitHub and grab anything you need. So you don't need to take notes because all of this will be available. So this is the agenda I have for today. We're going to start with a technology overview by myself. We'll run about an hour, and we're going to talk about what real-time digital twins are and why you should care, give you a little bit of a tour of our cloud-based streaming service, and then tell you about the software toolkit for building digital twins. And lastly, I'll give you a demonstration of the security application of a power grid on our streaming service. And then Brandon will then jump in and do a session in which he'll look at the actual source code for that demonstration and give you a tour of how you build Java-based real-time digital twins. It says here we're going to take a break after that, but based on the feedback I just got, I think we'll try to take a break between every session except the contact tracing, which only runs a few minutes. So after we do session 2 on Java-based real-time digital twins, we'll do session 3, which is a walkthrough of building a C# digital twin by Oleg, and this will be a digital twin for a wind turbine farm. So we'll get to see what a different digital twin application, and this one written in C# instead of Java. And next we'll do a demo by Olivier on a contact tracing demonstration application we wrote, which demonstrates how you can use real-time digital twins to track people within companies and quickly alert them and alert the managers when there's an exposure to COVID within a company. And this is a very interesting application and a very good use of digital twins. So that will be after session 3. And then we'll wrap up with the opportunity for you to build your own real-time digital twin. Hope you have downloaded the necessary API libraries from our site. You can go to our website and look in the user guide. And also we'll be explaining where they are and how to download them in sessions 2 and 3. But we're going to give you a little bit of a peek at that at the end of this session so you can get started while we're going through the Java and C# development. Lastly, I'll do a wrap up and thank you for attending. So let's get right into the technology overview. So this section here just explains to you some of the goals and challenges that we have seen in stream processing when you're trying to deal with a large number of data sources and monitor them in real time. And what we have developed over the last few years is a new software model for handling large numbers of data sources. We call it the real-time digital twin model. So we're going to explain how this came into being and why they're useful and how to actually build applications using this API model. So we're going to compare this to traditional approaches and show you some of the advantages, and show you some target use cases that we envision in real-time intelligent monitoring using real-time digital twins. And then we're going to look at how they are hosted on an in-memory data grid and how that allows them to scale and to offer capabilities that make it very easy for the application developer to focus on the application and let the in-memory data grid behind the scenes focus on the orchestration of messages and the scaling of the message processing. So we're then going to look at what it would take for an application developer like yourselves to develop a real-time digital twin model. And after I give you a brief tour of our streaming service, and we'll go look at the APIs at a very high level, a language independent level. And finally, I'll give you a demo of the security application we developed as a demonstration of the power of real-time digital twins when tracking large numbers of data sources. So just a little bit about our company, ScaleOut Software. We were founded in 2005, and we have been in this field of in-memory computing since then. And we've been very pleased to be part of the IMCS community for the last several years, and very excited to be with you again today. Our company focuses on scaling application performance and also providing real-time data parallel analytics and stream processing for fast-changing live data. And with that, well, that's the last of the commercial. The rest will be technical. So the real problem that you have in stream processing when you have a large number of data sources, and so the problems that we really have focused on is when you have thousands of data sources like cars or trucks in a fleet, or a farm of wind turbines, or a power grid with thousands of nodes, or smart cities application. And we'll look at some of the applications. They expand things as far as e-commerce when you're tracking shoppers, maybe 2 million shoppers on some of the largest websites, and you want to serve really relevant recommendations to those shoppers. Also, financial trading applications like tracking wire transfers and looking for fraud in real time. Also, disaster recovery when you're looking at, say, forest fires and you want to see where are the fires emerging and how are they moving so that you can react to them quickly. So there are many, many applications that have lots of data sources. And the challenge you have is how do you process this enormous amount of data that's flowing in, especially with 5G networks coming. We're going to see lots more data flowing in to a streaming analytics system. And then you want to analyze the incoming messages and events for patterns of interest and provide quick feedback to the data sources when applicable, and also to be able to look at the overall patterns and trends that are emerging so that you can respond in a strategic manner. So here's just a quick example of a medical refrigerator application. And in this application, you may find that there are thousands and thousands of medical refrigerators spread across the United States. This was in the news a couple of years ago when some of these refrigerators failed unexpectedly. They hold very, very important tissue samples, embryos, and other items which it's very costly if they're lost. So what you want to be able to do is track the behavior of every refrigerator so that you can predict its failures, doing predictive analytics for detecting failure before it occurs. And this gives you a chance to notify the user of that refrigerator to migrate the contents to another refrigerator. It also, a good streaming analytics system would be able to identify where the nearby refrigerators are located so that the amount of time required to find and move the items would be minimized. And at the same time, you want to avoid false positives. And also, if you have some kind of an aggregate problem like a power outage in a community that's affecting multiple hospitals, say, and affecting multiple refrigerators, you want to be able to react strategically to that and be able to migrate the contents perhaps to another town and do so in a very timely manner. So this is an example of tracking large numbers of devices simultaneously, trying to understand the behavior of each device independent of its neighbors, but also then be able to react strategically to a problem. So the problem that we have found is that streaming analytics platforms typically are pipeline or directed graph oriented. Going back to Apache Storm, more recently Flink and Beam, and some commercial products, what typically happens is that the event messages, I'll use the term events and messages interchangeably here today, these messages get pushed into an aggregated pipeline, and then the application developer writes code for these pipeline stages and passes the data through a pipeline, doing computation at each step to determine, to extract items of interest or patterns of interest out of the pipeline. And this creates a number of challenges. One challenge is simply complexity. How do you partition the work into a set of pipeline stages? How do you construct the graph? How do you then map that graph to a set of servers so that you can extract scalable throughput as you process the messages? And then how do you perform aggregate analytics? How do you find the patterns across all of the data sources without having to use an external data store? And then if you choose to use an external data store, how do you avoid scalability bottlenecks by having to access that data store? I'll show you a picture of that in a second. Here it is. So you can see that if you have an operation that's going to try to collect data and hold it for later analysis to give you context in which to process events, typically with a streaming pipeline, you need to go attach your own data store. Systems like Apama and Flink and Storm really require you to attach an external data store. They don't make the storing of context information about the data sources a first-class citizen of the streaming analytics architecture. They leave that to the developer to wire in the appropriate storage mechanism in order to meet the needs of the application. And the problem with that is it creates both complexity and a network bottleneck. So this is not really a problem if you're just looking at the data stream to extract patterns within that stream itself. But if you're trying to track contextual information about the data sources so you can introspect on what the data source is doing and why you're getting these messages, then you need to host this information in a cache or in a database, and then you have to be able to retrieve it very quickly so that you can analyze the messages as they flow through. And that creates these complexities and bottlenecks. So one of the problems with this bottleneck, as you can see here, is that it compromises scalable throughput. So as the workload goes up and you add servers to handle more and more workload, that is to say the message rate goes up, you need to handle more and more messages per second. You need to be able to access this external store even more quickly to handle all of that workload. And if you're crossing the network can become the bottleneck and compromise the ability of the system to scale and deliver linearly scalable throughput as the workload increases. This particular graph is not a stream processing workload, it's a financial services workload of backtesting stock portfolios, but it's the same issue, and that when you're retrieving data across the network from another storage mechanism, which is the blue chart here, the blue curve, you can see that the throughput stops scaling and can really fall off because of saturation of the network. Whereas if you can move the code to where the data lives, then you avoid the network bottleneck and you can have linearly scalable throughput. What that means is that the streaming pipeline needs to integrate storage within the pipeline in some fashion so that the data is immediately available without going across the network. And that's what real-time digital twins do. But this is an example of a system that is just trying to extract patterns in the data stream itself. And this complements what is done by real-time digital twins. It's not an alternative in our view. It's just another way of attacking the streaming analytics challenge. And it's a very interesting architecture in that what it does is it's looking at patterns and trends within the data stream. And I'll give you two examples here. In order to find out what the data stream itself is doing, but it's not trying to introspect on the behavior of the data sources. So what Azure Stream Analytics does is it uses a SQL view of the incoming messages. You can think about each message as being a row of a database, of a table in a database with a timestamp, and then the sequence of messages is the column of that table. And so you can do column-oriented time windowing analysis on that data stream with some very simple extensions to SQL. And so if you have an ad server application, you can, for example, count the number of ads served by product type in the last few minutes. That's a good example of that. And I guess when we're sharing screens, you're going to get to see all the pop-ups, so apologize for that. And then, but another example might be looking at a trucking fleet that's giving you speed telemetry from all the trucks. And so you could ask a question, what is the average speed for trucks in this region, so that you can look to see if there are any highway delays and know that you might have to reroute trucks, for example. So this kind of a streaming analytics platform will do that very, very nicely with a very nice SQL-oriented model. But the kinds of questions it's not going to be able to answer is, why is each individual data source sending the telemetry that it's sending? The trucks might be delayed for some reason, that because the driver is lost, or maybe there's a mechanical issue, or maybe there's a highway delay or a flooding event. So you don't know anything about what's behind the telemetry. Likewise, for the ad serving application, you don't really know why the users are viewing the ads they're viewing, what causes them to have that preference versus another preference. So it's hard to select ads that they should be seeing because you're just getting the raw data of what they are being shown. So this is sort of an example of the so-called Lambda architecture. This has been the classic stream processing architecture for more than a decade. And what it does is it separates this problem of stream processing into a speed layer and then a background data analytics batch layer. So what is done, what we just saw here is what's done in the speed layer. As the events come in, you can extract interesting artifacts about the events, and then you can respond to those. But you can't get the big picture, and you can't analyze the behavior of the data sources, because there's just, the architecture says what we really should do for those more complex computations is push that data to an offline data store, a data lake, if you will, and then do that in batch with a tool like Spark. And that's great. The only problem with that is that the results of this aggregate analysis are delayed. So for example, a typical trucking telematics application can process events from trucks and dump them into a database at a pretty high rate, but it can only just look at what that raw telemetry is saying. If you want to learn things about, say, the efficiency of the trucks in terms of their fuel burn and their on-time delivery, that kind of information is typically delayed by an hour or longer because of the fact that it's being pushed into a data lake for offline processing. And so what we really want to do is see how much more we can do in real time and be able to not only have the tactical view of what's coming in the data stream, but be able to look and introspect on the data sources, and then also be able to get an aggregate view of all of the data sources and do all of that in real time. So this is a way that people have tried to solve that problem prior to the real-time digital twin approach. What is often done is that an ad hoc network of services are combined to provide these capabilities, still leaving the aggregate analytics to offline batch processing typically by Spark today. So for example, a trucking fleet might have a set of front-end servers receiving events in the cloud from the sensor hubs on the trucks. And most trucks today, you may not know, are actually equipped with sensor hubs and do send telemetry through the wireless network, the cell network, to a cloud service. And these front-end servers then talk to application servers. It's not shown here specifically, but you can think of the first three as web servers, the second three as application servers. And what they do is they snapshot that data, they cache it, and they store it in a database. They display the cached information visually, and then the database is analyzed once an hour, or even take a longer delay, by a backend analytics service like Spark for visualization. So one of the problems with this approach is that it's complex and it requires lots of skills. You need front-end developers, you need middle-tier developers, people that know how to work application servers and distributed caches. You need database developers. Then, of course, you need specialized analytics developers who know how to use Scala to do Spark. So this is a complex, it can be costly in a cloud because you're using a lot of different cloud services. And of course, the delays still exist for aggregate data. So somebody should be muted who's not. So there's real-time digital twins were designed to address this challenge. And as I'll show you in the next slide, they really emerged from an existing use of digital twins in a field called product lifecycle management, or PLM. So they're a new, but we're using them for stream processing. So they're a new way to do stream processing by refactoring the problem to center on the state of the data sources instead of centering on the events and the message contents. So what they do is, at a high level, is they correlate telemetry from each device or data source and store that in an object which we host in an in-memory data grid. And then we take all the logic that would have been in the pipeline and we let the application developer create one method which encapsulates all of that application-specific logic and let that application just focus on a single data source instead of worrying about extracting events from the entire stream comprising of messages from all data sources. So you can track the state of this code, this application code, can focus on just on the messages from a given data source. It has instant access to state information, dynamic, evolving state information, so that it can do inferencing and introspection. We could use a rules engine or a machine learning algorithm in order to process that data, or you'll see some examples today of simple Java and C# for doing this task. And then another benefit you get is that all of these state objects then can be analyzed concurrently with stream processing to give you data parallel analytics that can be visualized and can provide feedback for processing incoming messages. So it's a very rich platform for processing incoming messages, and the insight is simply to correlate the events by data source so that you can maintain instantly available context for each data source, and also avoid the network bottlenecks, because we ship the messages to the server on which the data is being held. And that avoids network transfers during the execution of this code to go fetch this data. And then also, another big insight is that it's providing a domain for aggregate analysis. And I'll be talking more about that in a breakout talk on Thursday, aggregate analysis using digital twins. But for now, that's the big picture. I want to just actually go back for a second and compare that to the stream processing model we saw a minute ago. And so you can see, here it is, right there. You can see that what we've done is taken these programming steps and combined them into one code method that the application developer develops. We've let the developer ignore all but one data stream. And then we've also provided instant access to context for that data source with an object in memory hosted in the in-memory data grid. So it's a different approach, and it allows us to do some things that weren't possible before. So let's look at it a little more deeply. A real-time digital twin model, we have two terms we use, a real-time digital twin model, and then we talk about real-time digital twin instances. So a model, it describes both the algorithm you use to process incoming messages and what the properties are that you will be storing in a state object. And then for every data source, for example, for every wind turbine shown here, there is going to be a unique state object held that has the values of those properties for that data source. We call that an instance of a real-time digital twin. So this is the model of a real-time digital twin, and what we actually store is an instance for every data source. So if you have 10,000 windmills, wind turbines, then you'll have 10,000 state objects, but you'd only have one algorithm for processing messages. But of course, this will run independently for each state object when a message for that state object comes in, or a set of messages. So the message processor receives the events from, or messages and events from, that particular data source, this device typically, but it doesn't have to be a physical device. It could be a person who is, say, an e-commerce shopper, and this could be key clicks that are being registered by that shopper. So as telemetry comes in, this application-specific code is executed, and this code is written by the application developer and orchestrated by the streaming service or on premises. And this code will then take those messages as input, as parameters, and it will then process them, and will have immediate access to the state object corresponding to that particular data source. This state object is going to host information about that data source. Some of it can retrieve from a database, and other data it can calculate or derive in real time. Brandon will show you an example of deriving new property based on the telemetry and the values of properties that already exist in the state object. And so, as I said, there's one instance per data source. These things can be confusing, but we'll talk about real-time digital twin model, and then we talk about real-time digital twin instances. The application developer develops a model and then compiles that model and deploys it to the cloud service or on premises. And then once that model is deployed, these instances are created as messages flow in. And the creation of the message of the state objects as the messages flow in is automatically done by the platform. Now, one of the things that this code can do, it can access a database. It's going to get the messages from the data source. It can send messages back to the data source. It also can send alerts. It can send emails, and it can also receive commands from a user that could be sent through a REST interface directly to this code, and these messages can then be processed to command in turn the device itself. So let's move on. That's the big picture. And as I mentioned, this is a derivative of this concept of digital twins that have been used, I think, since 1990. I could be wrong. By Michael, originally conceived by Michael Grieves at the University of Michigan for product design and lifecycle management, PLM. And what the goal is in that field, and you can think of Boeing jets and building components for Boeing jets and making them fit together and work together and have the right protocols, and then be able to get telemetry to see how well they're performing in the field and whether aspects of them need to be redesigned. This is the business of PLM, and in this business, a model that actually models the behavior of that physical device is created. And there are also derivative uses of the digital twin that you can find today. And I just named 3 here. For example, the Azure IoT device twin. Azure also has a digital twin, which allows you to see spatial relationships between components, say, of an office building. You see the floors and then the rooms, and then you can see the light switches and where are the faucets and where are the chairs, and are the lights on or off. So this is a spatial model of a physical set of entities, but typically they're not targeted at real-time stream processing for intelligent real-time monitoring the way I'm describing today. However, the Digital Twin Consortium, which was recently formed, has come up with a definition for digital twins, which you can read here, and they accommodate the use of digital twins for stream processing in the second sentence, that they can also capture real-world behavior for analytics and learning. So this is the way we're using digital twins. I have another slide about how these two compare, but I think we could pretty much skip over that. You can read that in the slide deck if you're interested. It's interesting that digital twins can be used for simulation, both to model a device and also to send out messages that simulate its behavior and interaction with others. Real-time digital twins are really designed to react to messages coming in from the physical world. Notice that they're not a model of a device per se, but they are modeling the necessary aspects of that device in order to analyze its behavior and introspect and respond to it. So they do model the behavior to the extent necessary for streaming analytics, but they're not meant to be an emulation or a full model of every aspect of a device. So you can imagine how that would play out for various types of physical devices. So some of the advantages of this software model called real-time digital twins, what we've done is prepend digital twins with real-time in order to basically emphasize the fact they're for real-time streaming analytics and not for modeling and design. So real-time digital twins are a way to simplify the design of streaming analytics applications because they provide this automatic event correlation and they provide this automatic access to per device state or per data source state. These are two aspects of a streaming analytics application that no longer have to be implemented by the application developer because they're implemented by the platform. And the platform ensures that this is done with scalable performance and integrated high availability. So all of these aspects of the underlying platform can be simply handled automatically, and the developer only needs to think about what do I need to look for in the incoming telemetry and what context do I need to maintain so that I can introspect and respond in an effective way, and also generate derived contextual information that I can aggregate so that the managers can get a big picture about all of the data sources in real time. The other aspect that simplifies design is that they are, this meeting actually doesn't exist, or they use well-known object-oriented languages. There's no use of special languages or APIs or specialized hard to understand APIs. We have a very simple set of APIs, but they can be written in Java or C# or JavaScript currently. We're currently working on a rules engine, which we'll have available later, and then other ways in which real-time digital twins can be implemented by the application developer. One of the things we wanted to avoid is having a complex development platform that requires a steep learning curve to be climbed in order to develop any applications. So the benefit you get from this simplified application is actually deeper introspection on each individual data source than you could have gotten before, because now you can maintain context and access it immediately without delay. When I say without delay, we're talking about in about a millisecond, you can spin up the code with the context to analyze an incoming message and then be able to respond to it in another millisecond or two. So we're talking about responding to devices within a couple of milliseconds, 1 to 3 typically, and being able then to aggregate the state of all these digital twins and do MapReduce on them in something like 5 to 10 seconds. So we're talking about a very, very fast platform that's transparently scaling to handle very large numbers of data sources. And also, this real-time digital twin model, while it does not encapsulate in itself the domain-specific knowledge, for example, predictive analytics for an engine, it is the orchestration platform for that code. So the application developer brings that knowledge. For example, if you're looking at a trucking fleet and you'd want to determine whether a refrigerator on a truck is going to fail or an engine is going to fail, then the domain experts write the code that is placed in the digital twin in this process messages method, and the rest of the orchestration is handled by the platform. Okay, so what the net effect of that is that you get a much better introspection and ability to learn more about what the telemetry is telling you and be able to respond to it better. So one of the things that would be really nice to do is to know whether a driver of a truck has been driving too long or is accelerating laterally too much, and the sensors have that information, be able to judge whether this driver is erratic or tired or there's another problem. Also, whether or not as there are mechanical issues, be able to respond to them, be able to reroute trucks very quickly if a problem is spotted either with the truck or with the highway or with weather that's coming in, whatever the problem may be. And then to be able to see how all the trucks are doing in real time so that you can plan strategically to do reroutes or whatever is necessary in order to maintain the best on-time delivery and most fuel efficiency possible. So these are things that you can get with real-time digital twins because it's actually allowing you to track information about each individual data source, which in this case is a truck. And so then what happens is all these trucks in the field are reporting in to the cloud service. There's as many digital twins as there are trucks on the road. And then the aggregate analytics is feeding visualization, which can be then used by dispatchers to make strategic decisions. So I've touched on some of the other use cases, but let me just touch on one other one. Actually, I think I have a set of slides to go through it, but in general, we're talking about applications with many data sources. It doesn't have to be thousands, but it can be hundreds or thousands. Anytime it's too complex to try to extract this out of a data stream using traditional techniques, where it's convenient to have an independent context for every data source. And so typically we think these applications will have thousands of data sources, like medical refrigerators, like e-commerce shoppers, like smart cities, sensors, and so forth. And so the general category is real-time intelligent monitoring for situational awareness. So here's an example in a smart cities application where you're looking at perimeter sensors looking to see if there is a threat of break-in or a terrorist attack. So, you might have these sensors being triggered in multiple parts of the city, and they might be part of a coordinated attack, or maybe they're just independent and have nothing to do with each other. But the ability to understand what the sensors are telling you, to introspect on and eliminate false positives, and then to see with aggregate analytics where all the sources are merging and their time correlation allows you then to make a more strategic response than you otherwise could. Here's another example of real-time health tracking where you can imagine people wearing medical devices, and these devices are reporting important parameters about the user. They're not all athletes, as you might see here, but they could be people wearing pacemakers or other devices tracking heart effectiveness, blood pressure, blood oxygen, and so forth, and heart rate, and so forth. And so with knowledge of each individual's age, medical history, the current medications, current activity, and recent medical events, you can then introspect much better and predict whether or not that person needs to be alerted. And so that's another example where you have many, many data sources and where contextual information gives you a really good benefit. We talked a little bit about e-commerce recommendations. if you actually have context about each shopper while they're shopping, you can track what products they're shopping for, what are the attributes of those products, and be able to then determine by looking across their click stream as to what they're looking for in terms of price range, product preferences, brand preferences, product features, and be able to make very focused recommendations. This is typically not how recommendation engines work. They're typically looking to upsell and cross-sell so that they can maximize basket size. They're not looking at what is this person's looking for that they're not finding, and help them to find other products which actually match their needs. So you can imagine how that would be valuable. Also, if say there's a flash sale and you want to see how well it's doing, you can use aggregate analytics to measure the effectiveness of a flash sale. So getting back to the model, we see that real-time digital twins have shifted the focus from focusing on the events to focusing on the state of the data sources. And the left-hand diagram is focusing on the events. You're looking at the code, the application code is looking at all the events and trying to extract those patterns like we saw with Azure Stream Analytics. And that's extremely valuable when you want to understand what's going through the pipeline. For example, if you're looking to make stock trades, looking for stocks that say have changed their price by more than 5% in the last 20 minutes, this is a very good way to do that because you only need the immediate information. But if what you want to know instead is why has this particular stock changed its price, up or down? You know, was the CEO just fired? Was there a merger? You know, what events could have triggered it, and what does that tell us we need to do besides just track that stock price? Maybe we'll make a bigger sell or bigger buy based on that contextual information. So a state-focused view instead of an event-focused view gives you the opportunity to derive, to introspect on derived state that you're maintaining in memory and be able to respond more effectively. There's some other benefits of using object-oriented techniques for real-time digital twins. For example, you can build subclasses of base classes because it's just a standard set of classes. There's nothing fancy in the modeling definition. There's no particular structure beyond a class definition. You can, for example, have a defined, say, a basic controller digital twin and then build a hot water valve, which is a subclass of that. You also can build hierarchies of digital twins. For example, you might have hot water valves and circuit breakers within a pump room, and these can handle the physical devices, and then they can appear as abstractions to a higher level digital twin, which is, say, controlling the overall aspects of the pump room. And notice that we're showing that these also could be subclasses of basic of base classes for digital twins. And so by doing this, you can separate concerns. The hot water valve is just concerned with alerting if there's an issue with the valve. It doesn't know what a circuit breaker is, and it doesn't know what the pump room's characteristics need to be at any given time. So you can imagine on a ship, for example, you might have a hierarchy of digital twins so that you can very quickly assess problems in subsystems. You know, is it, you know, is the problem coming from the pump room? Is it coming from the engine room? Where is it coming from? The transmission? Whatever it is, you can be able to use hierarchies to abstract this problem in a hierarchical manner, the way you're used to doing with object-oriented programming. So this is an example of using real-time digital twins in a hierarchy for a wind turbine. You might have a twin for the blades, a twin for the generator, and another twin for the control panel. And then these two twins for the tower components are talking to a blade system digital twin. And this can all work recursively in the sense that messages that are being sent from this twin instance to this one look just like data source messages, and replies can be sent directly back as if these were physical devices. Likewise, the blade system can forward messages to the overall wind turbine controller, which is also receiving messages from the generator. I think spacecraft are another place in which this would be highly valuable, so that all the various systems can report upwards using a digital twin model and be able to very quickly in real time assess issues when you have to react in an appropriate way and very little time is available. And one of the cool things is you can then use this model to migrate logic to the edge. So as the controllers on the edge become more and more sophisticated and can do more processing, then the digital twins, which we just saw up in the cloud, can then migrate down to the edge and then send their telemetry up to the cloud. So you can migrate downwards as technology permits and as the network bandwidth permits, for example, with 5G networks. So this is another advantage. You don't have to rewrite that code. You just migrate the code and run it in a container at the edge. So for example, the sensor hubs on trucks are becoming powerful enough that some of the digital twins we run in the cloud could then migrate to the trucks themselves. So they avoid network bottlenecks because you can transparently scale by just adding more twins across servers in an in-memory data grid. You don't have to tune the overall software architecture to avoid network bottlenecks as you might with an architecture like Apache Storm. And so this bottleneck is eliminated because we're moving the, if you will, the code to the data. The messages go to the code, which is located where the data is, and as opposed to having to retrieve the data and bring it to the code as it's running. And so you see this nice transparent scaling that can scale to hundreds of thousands or a million instances of a real-time digital twin. But we're scaling by adding more digital twins to handle more data sources. And we're leveraging in-memory computing because we're running all of this within an in-memory data grid behind the scenes in our cloud service, as where there's an object for every digital twin. And we're scaling that grid transparently to the user who's only concerned about the devices and the logic to analyze what's going on. So if you want to open the covers up and see, well, what's actually going on under the covers, then you can see that the grid is hosting the objects, but in addition, there's a worker grid. I think this arrow works. Let me see. Yes. This worker grid is running the Java or C# code. So this is co-located. This code is running in, say, a Java virtual machine or a .NET runtime on the same server as the grid service. So all three of these are running on the same server. And this is 3 different servers being shown here. So this code is what's running the digital twin application code, the process messages code, which we'll look at a little bit more in a second. And so there's 2 processes involved here. And then there's a third process too for connecting to message brokers like Kafka or Azure IoT Hub. And this also is scaled by having a connector process on every server, which is feeding messages to the local objects. So as messages come in, you can actually tune Kafka to send the messages to the right server, or that is to say, have the right server pull messages from its broker corresponding to the objects that are locally hosted, and avoid unnecessary network transfers between the IG connector and the grid and the other grid hosts. So what you're trying to do here is minimize networking overhead so you can maximize the overall throughput of the system, and also achieve scalable performance by breaking these tasks up into the various processes needed to scale the overall message processing. And eventually we'll get to another slide. So we talked about accessing historical state. There's nothing that keeps the process messages application code from reaching into a database and retrieving state to complement what's in the real-time digital twin. So for example, device parameters, you'll see with the wind turbine example, how Oleg's code would conceptually goes to a database to find out the time to the next maintenance period, time to the next maintenance for a wind turbine, so it can compute the pre-maintenance period. And that would be unique for every wind turbine. And by accessing the database, you can get that knowledge. The contact tracing application, you can look up who is in a person's organization, so you can add them to the list of potentially exposed people if anybody in a particular team gets exposed. So there's the expectation is that these real-time digital twins will go to a database to achieve the information they need to process the messages. Likewise, they will push messages out to a database for archiving purposes. For example, to keep a full event message history if that's appropriate for the application. Might as well just say at this point, we designed this twin not to hold and buffer the messages indefinitely from a data source. We leave it to the application to decide which messages should be kept and which messages should be thrown away. And that allows real-time digital twins to be used for filtering. So you can see here that on the bottom diagram that messages might come in, say temperature messages from wind turbine, And you might want to filter all the messages except for the high temperature messages and the high RPM messages. So one of the roles of a digital twin can be to filter messages that go out either to a data lake or to a database. So we talked a little bit about aggregate analysis. What we're doing with aggregate analysis is simultaneously analyzing all of the instances that are held in the grid, selecting properties and combining them, aggregating them so that we can visualize trends that are happening across an entire population of data sources. Here are some examples of how this will boost situational awareness for the overall system. We talked about a flash sale and how you can look at what shoppers are buying. If you put some product on special, you can then do aggregate analysis for those shoppers that have that in their cart to see, did more shoppers put it in the cart, how long has it been kept in the cart, and how many conversions were made. That is an example. For wind turbines, you can spot whether or not more than one turbine is failing. Maybe there's a problem, there was a storm and it's caused multiple turbines to need repair, have cracks, whatever the problem might be. And so you can look at group behavior with aggregate analysis. We'll see this example, hopefully, of monitoring these nodes in a power grid, not for a rolling blackout, but to detect strategic intrusion into that grid. But the same thing could be used in a forest fire to detect where is the fire emerging relative to the power poles, and how fast is it moving in which direction, so that you can send emergency personnel to the right place as quickly as possible, and you can do the appropriate evacuations. And we talked about the fleets. So MapReduce is the technique we use to aggregate data across all of the instances of a digital twin by extracting information out of the state objects, and then first mapping it into groups which are defined by other properties. So for example, if you want to look at vehicle speed by county, then what you want to first do is map the vehicle speed data from all of the twins into the various counties. And that's what the mappers do. And they will map this to one set of data for each county. Say there are 3 counties here. And then, and so now you have the speed data by county, and then you can reduce it to find, say, the average value of this data. And now you have average speed per county. So that's what MapReduce lets you do. It's essentially a group by in Excel, and it allows people to then visualize data in an extremely useful way. And by integrating this into the in-memory data grid, you can do this while stream processing is taking place, while this data is live. And then you get to see the visualization. This might represent, for example, total severe incidents, I think by state here. And so you can see here, this is a measure of the behavior of a system, looking at the number of incidents that have occurred by state. And if one of these states has a higher set of incidents, if this bar goes up, this being refreshed every few seconds, then you know there's a problem, and that problem will need to be addressed. And that way people have enhanced situational awareness. All right, so our streaming service is called the ScaleOut Digital Twin Streaming Service, and it lets you build and deploy digital twin models into the service. And then it has built-in aggregate analytics that let you build widgets to visualize. And this picture here was of 2 widgets, we call them, in order to visualize the results of the aggregate analytics. And it's designed around an easy to use UI with integrated query as well. And then it also has so-called connectors that let you connect directly into your account on Azure IoT Hub or AWS IoT Core, Kafka, and it has a REST URL that you can send messages directly to digital twins through using REST. So it integrates into the Azure. It's not designed solely for use with Azure sources, but it is integrated into the Azure cloud. So it can connect to Azure IoT Hub or Azure Kafka, or out to AWS or through REST. And then it also runs alongside Azure Stream Analytics. So data might be taken by both Azure Stream Analytics and our streaming service simultaneously. And then we can either visualize aggregate analytics and directly, or we can push the visualization to Power BI for visualization, the way Azure does, Azure Stream Analytics. In addition, the service can push messages back through the hub back to the data sources. It also can be run on premises. using ScaleOut Stream Server. So you can get the same benefits of the cloud service on premises, and that way you avoid the use of the cloud service if that's appropriate for your application. So here's a quick tour, and then I'm going to show you this live, but just to give you a sense of what you're seeing. You first create a digital twin model using the APIs. You compile it into a zip file, which Brandon and Oleg will show you in a little while. And then you take that zip file and you upload it to the streaming service. And then you simply create the digital twin model, which gets deployed to the grid. And you can use Java, C# or JavaScript currently. The next thing is you can deploy a connector, one of the three we just talked about, or you can just use REST with an API key, which you can select through the UI. And this is an example of creating a connection with IoT Hub. And then you simply manage your models. You can restart them, delete them. You can get log messages from your code running in the model as appropriate, and be able to spot issues with your model. And then you can reach down and examine each instance of a real-time digital twin and look at what its property values are, so that at any time you can see how they're changing. And so, for example, if you're looking at RPM and it's changing, you can go look at the values and watch them change for each instance. And then you can develop widgets which allow you to display properties of these digital twin instances. You select a model, then you give your widget a name, then you select the type of chart you want to see, a bar chart or a line chart, and then you select the state field that you want to aggregate and the aggregation operator, and then a group by properties, for example, state, latitude, region, whatever, and then you just say save, and you to see it like that. And then you can drill down and query to look at for a given model, query all instances with a very simple, it's a SQL-like semantics with a UI-based formulation here. So you can say, I want to see these properties of all the instances, which are then displayed down here, based on these criteria, where you're looking at properties and selecting. These are essentially where clauses, which can be connected together. So the process is used as follows. This is an example where you're looking for shortfall in hospital supplies in real time. So if, say, hospitals are reporting messages to the service about their shortfalls in PPE, for example, then this can be aggregated and then shown in a bar chart, so you can see, well, hospitals in this region, in this region, in this region have the worst shortfalls, and we need to address them. And then you can go with the query and find out in a given region which are the hospitals that have the biggest needs, and you go address those needs, like these first two hospitals, because you know that's where the need is most pressing. And you can do various queries to hone in on what action should be taken based on that aggregate analytics. So now the last section of my part, which should be over in a few minutes, running a little bit late, is to talk about, at a very high level, how do you build and deploy real-time digital twins. So the first step is you use our ScaleOut digital twin builder library, and we have libraries in C# and Java and JavaScript, which you then compile and link to with your favorite development system, for example, Visual Studio for C#, and then you build a zip file, which is then uploaded to either the on-premises or the cloud deployment or the cloud service. So we'll talk more about that in just a minute, but the first step is to build your model and then deploy it, and then you start automatically handling event messages once it's deployed when the messages come in. So one of the things that's important is that every data source has a unique identifier, and that identifier is the basis for building a unique object in the grid corresponding to that data source. So when messages come in, the platform will build the digital twin object and let you initialize your variables, and then go ahead and process the messages for that data source and update the state of that real-time digital twin instance. So there's an instance of a digital twin for every data source. Now, one of the steps you do to get those messages is to connect to one of the various connectors we're supplying, or receive messages through REST. So the question comes up, why did we bother to build these APIs? why don't we just let people use the in-memory data grid and build their own digital twins in their favorite way with their own code? And the reason is because we're trying to eliminate a lot of complexity that would otherwise have to be done. And here are some of the areas of complexity that having these APIs allows you to eliminate. First, we are eliminating the managing and accessing of state objects. We are orchestrating the storage of those state objects and making them directly available through this API to the application code. So the user is no longer concerned about where is the object stored, and what keeps it highly available, where's it going to be, and how long does it take to get it, because it's instantly available when the code runs. We're also orchestrating the staging of the messages to the code that the application has developed in the digital twin model. So we direct the messages to the server on which the object lives, and then we run the process messages method written by the user. And all of the work to get the message there, both to handle the throughput required to send groups of messages and to handle high availability to ensure reliable delivery, is all handled by the platform. And so there are other areas in which we're adding value with these APIs. In particular, high availability is one for message delivery, high availability for state saving, and high availability for data parallel analytics to ensure that even if a server in our grid fails, the data parallel analytics continues to get processed reliably. So this allows the application developers to simply focus on defining the message processing code for each type of data source. That's a model. That is to say, creating a model, defining the dynamic state information that will be managed, and then to describe separately the data parallel analytics that will be used to extract information from that dynamic state and display it. So this is the API, but it fits on one slide, even though it seems to have gotten a little low here relative to the red line. So the application first defines, you'll see what I'm about to tell you applied for Java and then reapplied for C#. So this is the high-level foundation for this. The first thing that the developer does is define what a JSON serializable message type looks like. And it will typically have a type field so that various types of messages with subsets of the overall properties that are described in this message type can be supplied to the real-time digital twin model. So we use JSON serialization for incoming messages and also for storing state objects, by the way. So that's the only constraint we really place on those, both the state objects and the messages. The next thing the application developer does is implement an abstract base class called digital twin base to define the state object, and that's to hold the instance properties and perhaps event lists, which might be used by that application. So the idea here is that by defining this digital twin state object, then when messages are processed, those properties and the values of those properties can be delivered to that code and updated by that code. And where they appear is as the first parameter here of this method that's written by the application developers. We call it process messages. And it's given the state object, which it can update. It's given a thing called processing context, which we'll come back to. And then it's given a list of incoming messages that can be processed. So the processing context gives you helper APIs for things like sending messages back to the data source or to other twins, and for logging messages. And over time, we'll probably add more features to the processing context. But think of it as simply something that lives alongside the model to help the model process the messages and communicate with the outside world. It also serves to be the hook for creating a mock development environment. So we'll see the only difference between running this normally and running it in a mock development environment is that the processing context is changed to a mock processing context for doing development on your workstation. We'll get to that in the next slide or two. So the message list that's coming in has an innumerable list of messages that have arrived. And we decided to send messages in groups because that hides the latency. The hub will typically, like Azure IT Hub, will typically deliver multiple messages at a time. And by letting this process messages handle them in a group, you hide the latency of delivering messages and allows you to have overall higher message handling throughput and to do one acknowledgement for a group of messages. So the next step is to deploy it. When deploying on premises, we have APIs that are described in our documentation, and these are the same APIs that are used for deployment in a mock environment that allow you to simply specify the model and say build, and it gets deployed to the grid. But the more usual deployment is to the cloud service, and that's done by by using the API, the UI, and giving it a zip file which zips up this code that's described here and all its dependencies. And there's one extra file that we require for the model, which is it's called a model.json file, and it just has 4 fields which allow the runtime to find the various types that are used by the model when they're executed within the grid. And the next 2 sections, you'll see that JSON file in use in developing C# and Java models. So it's very simple. You just create a DLL, you then zip that up with the dependencies and a model.json, and you deliver that to the cloud UI, and it's deployed on the grid and it runs. So lastly, this mock development environment, what is that? What we learned is that when you try to do deployment directly to the cloud and you have bugs in your code, it's very cumbersome to go set breakpoints and examine state as a user of the cloud service. And so therefore, you can't really verify all the code paths before you actually are in production. So as an alternative, we built what's called a mock execution environment, and that runs on your workstation. So once you can compile the same model, but you replace the processing context with a mock version of same. And then when you finish building it, you can then write a test program which has features in this mock environment to send messages to a real-time digital twin model and to an instance of that model. And so if you send a message to instance 17, it will create an object in the mock execution environment and spin up the process messages code for that instance. And then you can then single step through the execution of your model, and you also can get access to the state, all the state variables, and be able to examine single step through and see that the code is running the way you expect it to. You can host about 100 real-time digital twin instances in the mock environment. And once you've then debugged it with test programs which send and receive messages, then you're ready to put it in production. So lastly, I'm going to do a quick demo of the simulated power grid, and then we'll take a break. And the section after that will be the Java section. So this power grid is simulating, the goal here is to show how you can get enhanced situational awareness with large numbers of data sources. And this is an application we cobbled together to show 20,000 simulated nodes within a power grid. So we have a load generator which is sending telemetry from these 20,000 nodes. There are 2 types of nodes. There's a so-called infrastructure node and a controller node, where the controller node is more mission critical. And these represent, these green dots and blue dots and all represent these nodes in the power grid and their last known state. So they report their current state. They're either offline or they're in a normal state, green, or they might be in some abnormal state, which they don't understand, or they might be suspecting there's been an attack to that node, or they might say, I absolutely know there is an attack, turn it red. And so this is the state, but the problem is these states can fluctuate, and there can be false positives, there can be flaky nodes. And so what you really want to be able to do is digest this over time, looking for false positives, and use other heuristics to make an evaluation of whether or not you think there really is a threat being posed to that node. And then you want to be able to aggregate that knowledge across all of the 20,000 nodes so that you can instantly report if you will, a curated set of information about the state of the overall network. So what we did was we created this one property and derived state called alert level, and you'll see this in the Java code. And it has an abstract range of 0 to 20. And what we're doing here is by examining the sequence of messages flowing through, we're updating this alert level using heuristics, mainly in this demonstration to show you how we can filter out false positives, and how if you move from a given state, like if you move repeatedly from say a normal to suspected attack and back to normal, back to suspected attack, there's a higher probability that there really is attack and a real attack than if you're moving from say offline to suspected attack, which might mean that the system's not working properly. So in any case, there are some heuristics that we put in there just to give you an idea of what it would be like to be able to write a real-time digital twin that could create a derived assessment of the state of this overall network based on looking at the raw telemetry. What this chart of the US is showing you is the raw telemetry, and then what the aggregate analytics will show you as the overall threat level. So there's a process messages code that's been created for this application and a state object, and these you'll see the Java versions of them, and it's pretty small code. And that's one of the things to show you is how small this code is for a digital twin. And then we'll show you the aggregate analytics that are running in real time, being updated every few seconds. And this is showing you the alert level by regions. We broke it up into 12 or 13 regions, and to show you so a manager of the network can find which regions have an issue right now. So before we do takeaways, let me try to give you a demo. I assume everybody can still hear me. Haven't heard anything in an hour, so I'm going with yes is the answer. Okay. So this is the demo running, and it's twinkles, but it's hard to see that it's changing. But every few seconds, you can see these dots are changing as these nodes are updating their state. And then here is the UI for the service. And what we have here is a digital twin model that we have been running, this Java model called Status Tracker. And you'll see the code for Status Tracker in the next section. And you can tell the connections in this case, there are no connections because of the fact that you'll see this is for another application. There are no connections for this because we're using an integrated load generator in order to drive a pretty heavy load, which we can see on the system status pane. It's driving about 1,900 messages a second to these 20,000 nodes, which are then 20,000 instances of real-time digital twins. And the amount of memory, it turns out, is relatively small. These are small messages as well, but it's illustrating that this message rate is coming in repeatedly from all of these nodes in the grid. So what we can do is we go to the dashboard and build a widget. Now this widget was created, and you can see it's updating every few seconds. So you'd say what kind of widget it is, and we're selecting alert level, which we found out here, which is one of the properties, and then we're going to maximize it by region. So another property is region, and so we selected region there, and we're not exporting into Power BI. And so then you have this widget, which is updating every few seconds. So now what we can do then is we can create an incident in order to make this more interesting. And this is going to be a simulated attack, hopefully, somewhere. You don't know where it is, and it would be hard for people looking at the raw data to assess the attack. But what happens here is we're aggregating this alert level, and notice it shot up to 20 in 3 regions. And that shows that our assessment from our derived state of alert level is indicating we really do have a problem in these 3 regions. We need to find out what it is and which nodes are being affected. So we can go to query here, and we can query to look at the incident count for those. This is looking in the Northwest region, which is one of those regions, and we can see which of the nodes are having the most incidents, which are having the severe incidents, and what is the false incident count. So we can make an assessment. IDs, or we use zip codes in this demonstration, but you can make an assessment here of what exactly is going on and be able to then take the appropriate action. So that's how you can use query in real time with the aggregate analytics on the dashboard. You can also examine the state. This actually takes some amount of time because there's a lot of state here, but once the state gets pulled in, then you can pick any random one once you pick one that you think is a problem, and then you can go look at all the state variables in real time. These are the actual Java properties that Brandon has coded for this application. So that is the application I wanted to show you. And let's see, let's go back to this. Okay, so let's wrap this up now. The takeaways from this section, this technology overview, is that traditional real-time stream processing makes it difficult and complex to track thousands of data sources independently, and it does not provide any natural way to track state or to have integrated real-time analytics. aggregate analytics. And the traditional Lambda architecture says, well, just do it offline. What we want to do is be able to do that online and complete it within a few seconds while we're doing deeper introspection on the data sources, be able to reply to them in a more effective way. And so the real-time digital twin model offers us a solution to these challenges, and it allows us to, the net benefit is enhanced situational awareness and the ability to respond more effectively to the data sources. And our in-memory data grid and cloud service gives you a platform for hosting and running these real-time digital twin models. So we're now done with session one, but we're not quite done before the break. So the next session will be a walkthrough of building a Java-based digital twin model. In particular, this status tracker you just saw, what we call it, you'll see the innards of it and how its implementation is done in Java. And you can ignore this break. We'll take a break after every section. But I want to first give you a preview of session 4, which is build your first digital twin. So this is what the programming challenge will be if you want to take part in it. And we also will have written the code ourselves, which is or will be posted to GitHub. So this is a very, very simple problem just to illustrate the mechanics of building a real-time digital twin model. It's not meant to be a representative model. So in natural gas sensors are picking up this potentially toxic natural gas leak that could occur in a house or in a factory or wherever, or an office building. And so if you go to the web, you'll find that the maximum allowable level is 50 parts per million for 15 minutes. And so you can imagine a gas sensor which is spitting out telemetry every minute, say, about the current parts per million. And so you want to write a digital twin which is going to process this telemetry and determine if a maximum exposure has been reached. The first thing you need to do is define the message type. So to write the class which defines the message type, which includes in it the ID, a current parts per million number, and a timestamp. And then when you want the model itself, the code that processes messages, to set a property, let's call it an alert flag property, when either it's observed that the gas level has been 50 parts per million for 15 minutes or more, or the level suddenly with one message just spikes to 200 parts per million, which is something we made up. The first part's real, the second part we made up, so you'd have it be a little more interesting. But if there's a spike like that, some spike, you want to be able to immediately set the alert flag. Otherwise, you want to be able to watch the sequence of messages, and if it goes above 50 and it goes below 50, you clear the state, and if it goes back above 50, you're in this alert period where you're waiting to see if it continues for 15 minutes of telemetry. And that gives you an idea of how we're deriving state information based on the raw telemetry. Now, there's a bonus too if you want to actually implement using the processing context to send a source to, if the alert level the alert flag gets set, to then send a message back. So you need to write a response message, which you send back to the source, the data source, which causes it to shut down the valve associated with that sensor. I want to introduce Brandon Ripley, Senior Software Engineer, who's going to talk about building a Java-based real-time digital twin. Brandon.
Okay. Sounds good. Let's jump into it. So just confirming real quick that you guys can all see the slides once it's full screen.
Can see it.
Okay, perfect. Okay, so my name is Brandon Ripley. I'm a software engineer at ScaleOut. And today we're going to be talking about the power grid demo that Bill just went through. What I've titled this session is Assessing Threats for the Power Grid. In addition to that, we'll be talking about very high level how to build the Java digital twin model and go through the APIs that programmers must develop or the implementations programmers must create. So quick overview and agenda. Let me just minimize webinar. There we go. That's a lot easier to read now. Quick overview. What we'll be talking about today is the Java digital twin model. We'll be going in depth on the Power Grid code example, and I'll be talking about the Java APIs and exactly what you need to do to get your first real-time digital twin model created. For me as a developer, one of the first things I like to learn about is all the places that I can go to for help. So I'll be showing the community forum as well as some other online web locations that you can access. to get up and running. After that, we'll do a quick dive on the digital twin APIs, and I'll walk through those, explaining exactly which classes need to be created so that you can create a digital twin model. After that, we'll spend the bulk of our time in the Power Grid code, and I will walk through all of the classes that we'll have to create, as well as exactly what we're doing inside of all of the business logic there. Once we're done with that, we'll wrap up and take some questions. So this slide should look pretty familiar to everyone. This is a slide that Bill just showed. This is talking about the Power Grid demo. The goal here was to demonstrate the value of enhanced situational awareness that you get when you use the digital twin model. So as Bill mentioned, what we're doing is we're simulating 20,000 nodes that are constantly streaming telemetry data into the real-time digital twin cloud service, where a status tracker digital twin model is running and evaluating that telemetry to update derived state that we call alert level. The alert level is simply an integer that has a value from 0 to 20 and is the orange suspected attack if it's above a certain level. So we'll jump into exactly how we update that in just a moment. So the big problem here is that we're trying to assess threats at scale. So we want to kind of figure out exactly what our challenges and solutions are there. So the big challenge here is that static state is not enough. We're not going to be able to inference, like Bill talked about in his session. We're not going to be able to inference just on the state in the object. The second problem that we find is that there are many data sources that we need to handle transparently with a scalable model. The third challenge is that we need real-time messaging. If we infer any sort of problem, we need to be able to get responses back to the data source as quickly as possible, all while being able to handle the real-time streaming telemetry from all of our thousands of data sources. So the solution is to use the real-time digital twin model. And the big reason here, or the big reasons here, are that we get derived operational state. So in the sample that I'll show you, we're calculating a heuristic known as alert level. We also get live automatic data source tracking. So the service will handle all data source management and storage, as well as tracking incoming messages to individual instances of digital twin state objects. And then in addition to that, we'll also get the real-time responsiveness by using the processing context, which allows us to send messages back to data sources after running calculations on the incoming messages as they relate to our state objects. So how do we do this? So the first thing we need to do is we need to create the status tracker model. So the status tracker model is comprised of three main classes: the digital twin base class, the message class, and the message processor. The digital twin base class is simply where we'll store all of our state variables, such as location, like we saw in the demo, the region, as well as longitude and latitude. For our message, this is going to closely represent our data source telemetry. So everything that the data source is going to tell the digital twin, we need to map into a message class. Once we've created our message, and our digital twin, we can create our message processor, and this is where the bulk of the code will be written. This is where we insert all of our business logic to introspect on both the digital twin instance, as well as the data source telemetry as it flows in. Next thing we need to do is test and deploy our model. One of the things that Bill mentioned is that testing in cloud environments can often be very frustrating, as what's in the cloud environment might be different from how it's tested locally. And we wanted to create a programmatic way to know that what you've developed locally will run either in the cloud environment or on a on-premise deployment. So we created this thing called the mock environment. And I'll go ahead and I'll explain that in detail later, but this allows you to have a fully functional runtime environment within your unit tests. Next thing we decided to do is create simplified configuration. So we call this the model.json, and this is simply where we specify the types of our digital twin, our message and message processor. Finally, we have to package it for deployment. And again, we wanted to create the simplest possible thing here. So all it is a zip file that contains your configuration file, the model.json. your jar that contains the classes for your digital twin message and message processor, and optionally any dependency jars that are required by your model. Once that's all done, you can take that zip file and deploy it to the cloud service or to an on-premise deployment. So now I will, actually, let me go back here. So here is where all of the code is available at github.com/scaleoutsoftware/digital twin demos. Underneath that, there's a subsection for Java, and then there's another subsection for the status tracker called Status Tracker. And you can download a Gradle project there to follow along with everything we'll go through. So while you go clone the repository, I will go through all those useful web locations that I talked about. So the first thing is to go to our website, scaleoutsoftware.com, navigate to support. And then the first thing I want to point out is the forum, where you can go to ask questions of the community as well as potentially members of our staff. If you go to documentation, there's 3 locations here that I'd like to highlight. We have the ScaleOut Digital Twin Streaming Service User's Guide. This explains all of the different pieces of the cloud service UI, as well as how to develop for the cloud service. Then we have the standard Java docs that I'll go over in just a minute for the Java APIs. And then lastly, we have the Java Projects Configuration Guide, which details how to create a Gradle or Maven project that connects to the ScaleOut Maven repository so that you can use our jars very easily. So this is the Digital Twin User's Guide. Here, under the API Libraries Java subsection, is some documentation that explains how to create a digital twin that's fully compilable. So you can just copy the code from here to get up and running immediately. Next, we have the Java docs. We're going to come back and talk about our digital twin core library in just a moment. Here is the Java project configuration guide, which simply describes how to set up Gradle and Maven to point to our Maven repository. This is our Maven repository. It's located at repo.scaleoutsoftware.com. Inside this repository, you could download the jars if you had a requirement to only use locally available jars. Next, we have a GitHub repository that houses the Java Digital Twin Core. You can go here if you're interested in looking at the open source classes there. And then lastly, here is the GitHub repository with the status tracker demo. So now I will jump into the status tracker project. So what we're looking at here is my IDE. I'm currently using IntelliJ, and I have a Gradle project loaded. So for this Gradle project, I have one compile time dependency that's for the digital twin core library. And I have one test compile time dependency for the mock environment. So if I jump back to the documentation, I can talk about the core API really quickly, and then we'll jump into the code. So there are a couple of classes here, but 2 that are really important for development and one that's important for how we process messages. So those 3 classes are the digital twin base, the message processor, and the processing context. The digital twin base class is the class that you'll implement that describes your state object in its entirety. This class will, in addition to what you write, you'll get 3 methods. You'll get getID, which returns the identifier for that digital twin. You'll have getModel, which returns the model for that digital twin. And you'll have an init method. The init method will be called the first time an instance of the digital twin receives a message. When that message comes in, you can do something like optionally load all of your context from a database or from some other cloud service. Next, we have the message processor. The message processor has one method to implement called process messages. This method takes as parameter the processing context, the state object, and the incoming messages. As you can see, both the state object and your messages will be strongly typed, so you'll need to define those before working on the message processor. The processing context is the next class that I want to talk about. And the processing context is how we get that real-time responsiveness. So the processing context provides the method send to data source, which allows digital twin a digital twin instance to immediately reply to its data source. So you could use this to do something like send an alert or tell the device to power off. In addition to that, we have some other helper methods here, such as send to digital twin, which is helpful when defining a hierarchical set of digital twins using an object-oriented model. And then we're also able to log a message if we ever wanted to put something in the status window in the UI. So now let's jump back to the code. We'll go ahead and close our build.gradle and we'll jump into the status tracker. So this is the status tracker, which is the digital twin class. This extends the digital twin base, and here's where we'll store all of our state variables. So for static state, we have things like the node type, the node condition, the region, the longitude, and the latitude. So the node type refers to what Bill mentioned earlier. We simulate two types of nodes. One is infrastructure and one is a controller, where controller nodes are considered high priority or more important. And this allows us to have different types of nodes that we're storing with one model. In addition to all our static information, we also have our derived state variables. So the one that we mentioned in the demo is the alert level. This is that integer that ranges from 0 to 20. And in addition to that, we have a number of counts that we use as a heuristic for deriving this alert level. Excuse me. In addition to these derived state variables, we also include a dynamic incident report list. This dynamic incident report list is not used as in the demo, but it's used for demonstration purposes to show that as we receive unexpected events, we can record them so that they could be viewed at a later time. Next, we'll move on to the status tracker message. Inside the status tracker message, we're going to define a number of properties that we will analyze as they come into the message processor. So the properties that we have here are the type, the ID, the node condition, the node type, the region, the latitude, and the longitude. So as Bill mentioned, both the digital twin instances and the messages sent to instances are JSON serializable. And one of the things that I want to talk about here is why that's useful. So what we can do with the status tracker message is we can encode a type in here so that we can only extract certain properties from the message and exclude them if we don't need them. So jumping over to the status tracker message processor, I'll go make that a little bit smaller so we can read it all. Here we have the status tracker message processor, and that is a implementation of the message processor with our strongly typed status tracker and our strongly typed status tracker message. And then we have our implementation of the process messages method. Here we see that the parameters are processing context, our instance of a instance of a digital twin, and the iterable list of messages. So before we jump into the code, I want to show how simple that this code really is. At its very core, this is a try catch that wraps a for loop and determines whether or not to update the digital twin. So in terms of development, the code is very simple and easy to write as well as manage. So if I open this loop back up, we'll talk about everything we do in the message processor. So if we look at this first if statement, what we're doing is we're checking the message to see if it's an initialization message. So this is what I was mentioning back when we were looking at the status tracker message. We're able to look at the type of message and then pull the properties that we need from that message. So what we're doing here is we're setting the instance of this digital twin for the tracker type based on the message. We're setting the status tracker condition based on the message. And then we're also setting the region information, the longitude information, and latitude information from the message. And then we immediately return telling the service to persist our digital twin. Once we've gone through our first initialization message, what we can do is we can run through the status tracker rules. So this is where we start trying to derive state based on, starting to try to derive the alert level variable. So the first thing we're going to look at is we're going to try to determine if everything's okay. So if the message indicates that the data source is offline, or if the message indicates that we're in normal operation, we then need to introspect on the state of the digital twin. If the digital twin instance is currently experiencing a minor event or a moderate event, we're going to consider this a false alarm and increment the number of resolved incidents. However, if the digital twin is currently experiencing a severe event, we're just going to consider this resolved and not a false alarm. And that indicates that we had previously seen a severe event. After that, we'll update the alert level, set it back to normal, and set the status tracker condition to the condition that the message sent in. The next two rules are very similar. The first rule is saying if the message indicates a minor incident, then we'll set the alert level to the minor alert level for both a controller and an infrastructure. We'll increment the minor event count, and then we'll set the status tracker condition based on the message's node condition. And we're going to do that in both cases, one for severe, one for minor. When we start looking at moderate incidents, this is where we want to really derive the heuristic for alert level to see if we're suspecting an attack. If we look at the message and we see that it's a moderate incident and that digital twin severe incident count is greater than 0, this means historically we've seen that this node has been attacked. We want to set the alert level to a moderate, but we also want to set it to a little extra because it's a little bit more than moderate because we have seen severe incidents in the past. And we'll go ahead and do that for both infrastructure and controller nodes. Next rule, if we see that the message indicates a moderate incident and the digital twin get severe incident count 0, that means we haven't seen one in the past, and we have also never seen false incident counts, that's also 0, then we'll once again want to set the moderate, we'll want to use the base moderate alert level, but increase it by another constant value to indicate that we are suspecting something might be going on. Next, we'll want to check the message for a moderate incident. If we see a moderate incident, if we see the severe incident count is 0, but we have seen a number of moderate incident counts, meaning we've seen moderate incidents before in the past, then we want to get the heuristic for the number of false incidents relative to moderate incident counts. And if that number is greater than 50%, we're going to set the alert level again, but just a little bit extra because we are worried that we're suspecting an attack. The final rule, and the one with the highest level of suspicion, is if we see a message that indicates a moderate incident, if the digital twin has never seen a severe incident, and if the moderate incident count is greater than 0, we're going to once again look at the heuristic for false incident count relative to moderate incident count. And if that's less than 50%, we'll increase the alert level to our highest level of suspicion, which is moderate +4. And then in each of these cases, we'll be incrementing the moderate event count and then setting the status tracker condition to the message node condition. The final rule is that if we see any type of incident, we want to increment our total incidents and add the incident to the incident list. And this, as I explained earlier, is a member of the state object where we can see an incident report list. Once that's completed, we'll return processing result.update digital twin to persist the state of the state object. So now that we've created all 3 classes, we can go to the top of this function again and navigate to the test processor. So the test processor is just a member of my project called test processor. So it's in my unit testing folder. And what we'll be doing here is we'll be testing the status tracker model within the mock environment. So before we do that, let's jump back over to the documentation so I can explain all of the classes there. So inside of the mock API, we have 4 classes: the mock endpoint, mock environment builder, and mock log message. The mock environment builder is used to add your digital twin as well as build the mock environment. The mock environment is used to retrieve instances of the digital twin as well as get logged messages and generate the model schema. And then one of the very important classes here is the mock endpoint, which has some static methods on it for sending and receiving messages to and from digital twins. So now we can go back to the code, and I will walk through this very simple unit test where we're trying to test the initialization message. So what we see here is that we're creating a new instance of the mock environment builder. We're adding a digital twin. We're defining the name as status tracker. We're creating a new instance of our message processor. We're telling the service about the status tracker, which is our digital twin class. And then we're telling the service about our status tracker message. And then we're building the environment. And this will give us an instance of the mock environment that we can use. So next we'll need to create our serialization framework. For this example, I'm just using JSON, but you can use any JSON serialization framework. I'm going to create a init message, which is a status tracker message where I've set the type to init. I'm going to send it to instance ID 23. I'm going to set its region to the northwest. I'm going to set its condition to normal, and I'm going to set its node type to controller. After that, I'm going to set its latitude and its longitude, and then I will serialize the message and then send it. So what I'm doing here is I'm calling the static method on mock endpoint send. I'm sending it to the model status tracker, and I'm going to send it to the status tracker instance 23. And then last, I send the message. What I'm doing here is I'm just validating that the result returned from mock endpoint.send is handled. And that's just to make sure that everything worked as expected. But that's not quite enough. I also want to validate that what occurred within the environment is exactly as I expect. So I'm going to, from the mock environment, retrieve all of the instances for our model status tracker. And that gives me a nice hash map of IDs to digital twin base instances. And then I'm going to pull out the actual instance that was created by the environment called, I'm just going to call that actual, and I'm going to be retrieving the ID 23. Next, I'm going to create the status tracker that I expect. I'm going to set its status tracker type to the initialization message type or node type. And then I'm going to do the same thing for node condition, for region, for longitude, and for latitude. And if that looks familiar, it's because it's our very first rule. So I'm basically just validating that this if statement is getting hit. So now we can go ahead and run this test, and we happily see that our unit test passed. But in some cases where it's not easy to determine the state, we might want to actually go through and debug. So we'll go ahead, right-click our method, and click debug. So now I can see that inside of my process messages method, the breakpoint that I set was hit, and if required, I can look at everything here. So I can look at a brand new instance of the status tracker, see that everything comes out as being newly initialized. I can look at the messages and see that I have a single message coming in. The type is init, the ID is 23, node condition is normal, controller, region is northwest, and those look like the latitude and longitude that I set up in my test. So if necessary, I can step through this if I was trying to find a bug, but we're not looking for a bug right now, which is great. So that's the first test, and that's how to use the mock environment to navigate through what's actually being stored by the service. But one more thing is that we want to make deployment easy once the mock environment has passed all of the tests that you throw at it. And to do this, we're going to use the generate model schema method. So once again, I'm going to create the mock environment builder. I'm going to add our digital twin. I'm setting it to the status tracker name. I'm once again supplying a new instance of the status tracker message processor. I'm assigning the status tracker class and the status tracker message class, and then I will build that builder to return a new instance of the mock environment. From that environment, I can call generate model schema and pass in our digital twin model name, which is status tracker. And then optionally, you can supply the output directory, which I've set here as just my desktop so that we can look at it. So if I go ahead and run this, it will pass. I can navigate to my desktop. I can right click and open this in Notepad++. And originally it comes out without formatting, so I'm just going to format it so it's easier to look at. Give me one moment. So now what we're looking at here is the model.json configuration file. So what we see here is 4 properties: model type, message processor type, message type, and assembly name. So assembly name is an unused property by Java and JavaScript models, but we've gone ahead and included it just for completeness. So in the model type here, what we see as the value is the fully qualified class name for the status tracker. We see the same thing for our status tracker message processor. It's always the fully qualified name. And for the message type, it's the same thing, the fully qualified name for the status tracker message. So as promised in the slides, deployment is as easy as taking our build output and the model.json, adding it to a zip file, and deploying it to the cloud service. So we'll go ahead and do that now. So what I've done here is I've gone to my Gradle build output directory. I've grabbed my jar that was created, and I've copied it over to my desktop where I have the model.json configuration file and now the status tracker jar. I'll go ahead and zip those up, and I will not call it desktop.zip, I will call it status tracker.zip. And once I'm done with that, I will navigate to the cloud service. I'll go ahead and log in. And then I can deploy my model. So it looks like something else was going on here. So I'll go to create. I'll supply the model name as status tracker. For the language, I'll use Java. For the resource file, I'll navigate to my desktop and select status tracker.zip and hit open. And I'll do deploy when created. This deploy when created toggle indicates to the service that once it's saved to the service, it also should start running immediately. So I'll go ahead and hit create to get that started. And now our digital twin model is successfully deployed to the cloud service. So if I go to manage, I can click on the status tracker model name and see that our status is running. And I can look at status and see that digital twin added and deployed with our name, status tracker. So if we jump back to the slides, that concludes most of the code demo. So to conclude, what we did through this session is we showed some useful web locations. We showed the community forum as well as some guides that will help you get up and running, creating your own digital twin models. We gave a big overview of the Java digital twin model, describing the classes that you'll need to implement. We created the status tracker digital twin model. We tested the status tracker digital twin model within the mock environment API and showed how to run some simple unit tests. And then lastly, we deployed the status tracker digital twin model to the cloud service. So I've included all of the resources that I showed in this session as a part of one of the slides. And again, these slides are all available on the Digital Twin Demos GitHub repository. So if you're interested, you can go click on any of these links and they will take you directly to the web locations. And that concludes my time.
Thank you, Brandon. That was a really excellent talk. I'd like to introduce Oleg Shmytov, our Senior Director of Engineering, who will talk to you about building real-time digital twin models using C# with an example using wind turbines. Go ahead, Oleg.
Oh, thank you, Bill. Yes, we'll take a look at the creation of the real-time digital twin for .NET runtime, and we'll use wind turbine as an example. And my name is Oleg Shmytov again, managing the engineering team at ScaleOut Software. Here's the agenda for my brief talk. We'll talk about we'll overview the wind turbine model. Well, based on that, we'll talk about the goals, so reiterate the goals again for real digital twins. And we'll also look at the basic principle principles of creating the twin models in C# specifically. We'll look at the code of the wind turbine project. Then we can look at the set of NuGet package we publish, which would help you in development process. Some of them contains the basic classes and mock environment, which Brandon touched based on in the previous session. Some of them would be new. We'll look how to debug the C# code in mock environment in Visual Studio. I'm using Visual Studio 2019. And then we'll deploy that digital twin to the cloud environment. And I'll show you how to process messages from Azure IoT Hub by that specific model. We'll take a brief look at how to set up Azure and what parameters we have to use when we're setting up the Azure IoT Hub, and specifically how to register devices, and then how to drive the load through the Azure IoT Hub and process the messages within the model. So that's the agenda. So first, let's take a look why the wind turbine. It's a example of device which is very expensive, large, and the goal for us here to predict the failure, to prevent the expensive failure and repairment. So there are a few issues in real life you can see you can have with the wind turbine. It could be the high temperature could cause the fire, it could be vibration, etc. So so the goal would be to again build a model to track the behavior of that device as a data source, and we'll show how to do that. So what our library, digital twin library, brings to the table and the whole technology is it allows you to correlate the telemetry emitted by each entity, by each device, correlate to the real-time digital twin in the data grid. Also allows you to store, the digital twin allows you to store device-specific information, specific model characteristic, maybe the service history records and other requirements within the twin as a state of each individual instance of digital twin, as well as by tracking the events, you can derive the state from inferencing the, from introspecting the incoming messages. So by introspecting the messaging, you can detect the failure conditions similar to what status tracker demo showed. You can have a set of rules or more complex rules engine which would analyze your data. And in this particular case, we will look for overtemp condition. I'll show you the code how we would do that. And then based on the type of the twin model and maybe their characteristic, we can adjust the time when that overtemp condition allowed to have before we call it as a failure or pre-failure condition we want to report on. So, and of course, in addition to that, the model, our runtime allows us to scale thousands and tens of thousands devices easily without any work from the developer side. So we will scale it using the in-memory data grid platform on the back. So the sample application I already mentioned illustrate the use of digital twin specifically to track the temperature. So we'll see it in the code. The digital twin model here tracks the model specific type and maybe pre-maintenance period, various temperature numbers, the maximum temperature numbers and level, and the current temperature, both for normal and pre-maintenance condition. Let's assume maybe some of those devices are in pre-maintenance mode, so that would affect the algorithm. And of course, we will derive the state based on that information. So, so when we see the message, when the number of messages with the high temperature continues to flow during a predefined period of interval, let's say in real life 10 minutes, and if steadily grow, then at the end of that time, we can declare the failure, the high temperature failure mode, and we'll send the alert back to the management team, and then we'll also be able to send the specific command to shut down the turbine or change some of those parameters within the turbine itself. And then we can, of course, log the incidents as they come for the time window analysis. So we can know, for example, how many incidents per hour we have for individual turbine, and then we can use the aggregate analysis later to derive the global knowledge about maybe what the characteristics per each farm we have. So let's take a look on the digital twin model class itself. It's a simple class which contains some of the static parameters which define the physical characteristics of the device itself and maybe some thresholds, as well as some dynamically changing state, which we can divide as we analyze and introspect the incoming messages. So we can also optionally save the list of messages as a part of that class, as well as the list of incidents. So before we look at the code, let me show you the documentation. As Brandon already showed, the documentation is located on our website under the support documentation section, and there is a real digital twin section on the left. If we click the user guide and open the API library section, which is .NET specific, you can read how to define the model. So the model consists of 3 classes. One is the state object, or the digital twin class itself. It's actually listed over here. So the only one requirement here, you need to inherit from our base class. It's an abstract base class, digital twin base class, defined in the NuGet package we publish on NuGet.org called ScaleOut streaming.digitaltwin.core. So that package you add to your Visual Studio project, and it delivers all the necessary base classes you need to have when you're defining your model. So documentation about all those base classes also available on our website is here. So let's take a look. This is the full .NET API reference. And talking about .NET Core, NuGet package, it contains definition of digital twin base class. It also contains the message processor class you will inherit from when you define your own message processor for your model, as well as the processing context class to control the dynamic behavior of your model. Coming back to the Visual Studio now, so the project itself, it's a .NET standard project, which has a list of classes, and the class I showed you on the screen before, it is the wind turbine digital twin class. This is the full definition of that versus what we've seen in the slide. It was just a subset of that. But the important message I want to come back to the slide is once you define the state information and you come to the message processor, which is the next slide over here, this is where the bulk of your logic goes to. So the message processor class inherit from our main, our abstract-based message processor class, and the process messages method That's the only method you need to override. So it consists of the, that's where you would typically do the processing of your messages. You get the processing context, the instance of your digital twin, as well as the list of incoming messages. And you run the logic as Brandon showed in Java. The same principle apply for C#. So specifically for wind turbine, we want to check when the message comes with the high temperature which exceeds our threshold. That indicates we start tracking the overtime condition. So if the message comes in and next time with the low temperature we exiting that condition, so we only track condition which continuing, which is all the high temperature parameters are continuing over a certain period of time. So this is how we track the overtime condition on that slide. It shows the gist of the code. So the idea here that as long as we receive the messages with the high temperature, we store those messages as an incident, and then if it exceeds the threshold, the time allowed for high temperature messages, then we create alert and send the control message to the data source. And then if we stop receiving the high temperature within that conditional window, then we exit in that mode and we clear the state of our digital twin. So coming back to the Visual Studio, over here, I want to show you the, in addition to that, the message processor class, which you've seen on the slide. It looks almost identical. So this is the all the logic exists. So we added all the logic for high temperature in a separate method, as well as with tracking for low RPM condition as a bonus. And then we run another message after we another method to calculate the averages for last 24 hours using our time windowing library, which is another NuGet package you can download from our from the NuGet.org. So let me open our website and our documentation. So once you define digital twin model and you define the message right here, which could be any POCO C# class with the properties that represent the state of your, the telemetry of your device. Then you can start your testing model. This is the message processor we've seen. In order to start testing, you need to download one more NuGet package called scaleout.streaming.digitaltwin.mock. So typically you would use maybe a unit test environment. You add that NuGet package to the unit test environment and you start exercising your model. So let's do that together. So I have a separate mock unit test project, and I created a few unit test methods using that NuGet package library. Let me show you what library it references. So the ScaleOut streaming.core and .mock. It has some. It also references the one more NuGet package, digitaltwin.common, which has additional components which are used by that unit test. But in the very basic view, the way how you instantiate the model and start using that, similar to Java API, you create a mock environment builder. You add your digital twin by specifying 3 types we just defined, and then you call build. After you maybe send some messages and use that model during the test or during the testing exercise, then you shut it down. So let's take a look on extended version of that usage. So here we're creating the same model, and we load that runtime, load the model into the runtime, and we will going to send a message to that model using the mock endpoint don't send. So the mock endpoint is a part of the mock environment NuGet package. Let me switch back to the documentation, and let's take a look what that NuGet package contains. So the mock environment builder allows you to create the environment and add your model there. It also allows you to generate the model schema first time, and then you can also retrieve the messages which are targeted from another twins to that model instance class. The mock endpoint class allows you to send messages to specific digital twin, as well as the receive messages which are sent from that twin to the data source. So let's exercise that method together. So if we can run that specific unit test, as you can see in the test explorer, one test is passed. But I want to put a breakpoint and see what happens within that model itself. So we'll repeat that test again. We'll stop it at that. So we'll continue. Oh, that's a release. Let's just switch to debug version so we can have a full experience in debug environment. Start that unit test again. We'll stop before we're going to send the message. As you can see, we send the message called device telemetry. And we deliberately set the temperature above the threshold which we're looking for. We were going to determine that as an incident because the temperature is too high for that. But we'll put a breakpoint on the message processor class within the process messages so we can see that message comes into our model. And then within the loop, so it's one message we'll process, and the track for high temperature method should detect it is a message with high processor. It enables the overtemp condition for us. So, and then let's come back to the unit test and put a breakpoint at the very end when we retrieve that instance to see whether that was the case. So when the instance is received, we can also inspect its state and see, yeah, indeed the high temperature the mode was started at that time, and we have one message which was the parameter we just sent above, and that was 120-degree message. So then we shut down that environment, and that shows how to polish the code within your model, troubleshoot the problems, and be ready to deploy to the real-time environment. As Brandon mentioned, before we deploy that model, we want to create a JSON file which describes that model for our cloud service runtime. So we're going to need we need to build a JSON file which describes the model. It consists of 4 elements. It's a full qualifying namespace dot class name string values here, and the assembly name is used to indicate in the zip file we're going to create what assembly contains all those types. So we'll introspect that assembly and we'll find all those types and instantiate those types in real time in the cloud environment. So let's create a zip file as Brandon and Bill mentioned. In order to deploy to our cloud service, we need to compile the model, add that JSON file, create a zip file, and upload through the UI. As simple as that. So when we're going to build, if we use .NET framework, .NET standard type of the project, there's one more step we need to do to force Visual Studio to produce all the dependent files in the output folder. So I can show you what setting to set in that particular project. So let's unload the project and see that in XML here. And the setting I'm talking about is that copy local log file assemblies. So we need to set it to true. That forces Visual Studio to compile the .NET Standard project and output all the dependencies into the output folder. So once we compile, let's switch to release back, compile it, and open the folder. So we can see in the release folder now, we have all the output. So we'll create that zip in a second. So the wind turbine JSON file, the assembly itself, and 3 dependent assembly, digital twin.core, newtonsoft.json, and time window in DLL, which came from another ScaleOut NuGet package for time window analysis. So let's create a zip file and call it wind turbine. Remember the path, and let's switch to our service. So let's go to the browser. Let's log into our cloud service. Go to create, select type the model name, which is wind turbine, select the runtime.net, browse to that location where we have our zip file. And that switch tells that when the model is created within our environment, it immediately deployed, which means it's enable for message processing. It can handle the input. So once we deploy it, we can check the state of that. It is running, so which means it's deployed. So now let's take a look how we can feed that model with the messages and ask them to process them. So for that purpose, we will use the Azure IoT Hub. And in order to use Azure IoT Hub, you use Microsoft Azure Portal, create that as a resource, and this is the place where you registered all your devices. So I have 5 hypothetical wind turbine devices registered here. Each of them will have specific parameters, primary key, and which you would need to use in the application, which is going to send data on behalf of that device. And here, there are some other parameters you would need to use. So we recommend you to create a dedicated consumer group where we will listen for those messages, and I can show you where to use. We'll use the demo secure consumer group. That's part of the Azure IoT Hub. And there are some other event connection strings over here we can use when we create that connection in our UI. So let's go to connections section, and we'll create a new Azure IoT Hub connection. So this is where we can call our connection. Let's call it IMC Summit. And the Azure IoT Hub, I have Oleg Hub as my hub name. There are other parameters. I will skip deliberately for them so you can read them from the various section of your Azure IoT Hub. That's where the demo consumer group goes. And here the batch size, it allows you to indicate how many messages you might have in one delivery to your model. So in this case, we'll say, oh, let's do 55. Let's create that connection. And now if we look at the state of that connection, it is running and listening for messages from the Azure IoT Hub. So the next step is to send messages to the Azure IoT Hub so they can go through the hub and be delivered to our model so we can start tracking the temperature. So that solution, which is published on the GitHub repository we shared the link for, also contains the simple Azure client application, which shows you how to send messages to the Azure IoT Hub. So it instantiates the simulated Azure device class over here, and it will send messages to the Azure IoT Hub, and Azure IoT Hub will relay those messages back to our model since we have that connector. So our connector listens for the messages, and once they arrive, they will deliver to the appropriate instances. And if the first message comes in, if instance doesn't exist, it will create that instance and deliver the message for processing. So let's start that up. And it allows us to send the high temperature message or low RPM message, or random messages. So we'll do that in a second, but first let's take a look on our dashboard. So I created the dashboard, which has a history here. So we'll have 5 devices registered. So let's start sending the high temperature messages. And that should be reflected on that widget. We can look what that widget does, but the widget actually shows, displays the number of high temperature messages which each individual instance received. So, and if you can look at that application, at a certain point when we reach that threshold, which for model in the normal condition, I'm modeling here, it's 20 seconds, but for the pre-maintenance condition, it's 10 seconds. It's a duration of the overtime condition we allow before we call it is a problem. So at that time, we send message back to the data source, and my program here plays the role of that data source, plays the role of that wind turbine. So the command I'm sending is just shut down command, and I'm receiving that in a separate application, even my model right now running in the cloud. So that application running on my local PC here in the office, but the model is deployed into the Azure cloud, and I'm able to receive the message through the Azure IoT Hub back to my application, and that message, alert message says, oh, I have high temperature, and it tells me the wind turbine 5 specifically, which is message I'm receiving on wind turbine 5, has that problem. So that illustrates the power of the technology. So we can tie it together components running in different regions and different environments. So if you look at the widgets, similar to what Brandon showed you, it just tracks the number of messages with the overtemp. And since I deliberately send the high temperature messages, each of those 5 wind turbine instances receive those messages. So we see all those lines, and we can query. Let's do the high overtemp, and then maybe the ID. So we can see how many messages each instance received during my test interval when I was pressing the high temperature button over here. So if we send a little bit more and rerun the query, we'll see the number change. So in real time, those model instances processing those messages and try to derive the state, the high temperature state, and report back to the turbine and back to me as a operator of that wind turbine farm, for example. So that's the power of technology. So let me switch back to the slide here. So that was demo. So Lastly, I want to leave you with the links, and you can explore the more NuGet packages using that link. They are all published on the NuGet.org. There are some other NuGet packages you might want to look. And if you have any questions, don't hesitate to send me email after the session. And on that, I'm
Okay, well, Oleg, thank you very much. That was excellent. So now I think if you can hand it over to Olivier, we'll do the contact tracing demonstration, and then we'll go back to Oleg to,
yes.
We'll take a break after that and go back to, but Oleg will put up the slide, I think it's slide 6, which will show that we're going to do the sample programming exercise at the very end. Okay, so Olivier, please take it away. Thank you. Once Oleg gives you the screen.
Just leave it.
Thank you, Oleg. I'm going to share my desktop. I am somehow not seeing the button.
I don't think that the screen has been shared, making you a presenter. Did you, Oleg, were you able to make Olivier a presenter?
Let me try it again.
Or maybe I can do it. I'm going to do it myself here. I think I can do it. Olivier, here you go.
Oh, okay. Now I can see that. So, can you guys see my the presentation right now?
Yes.
Yes, we see it now.
All right. So thanks. So by now you probably have a good idea of how to implement a digital twin, and you are going to get to actually play with that after this. But we wanted to show you one more demo, one application to a really modern problem, which is contact tracing. Contact tracing, if you're not familiar with it, it has been used for decades by health departments to slow down or stop the spread of infectious diseases, mostly by tracking people who have been in contact with infected people during a pandemic, and this is a very tedious and manual process that can take a very long time when you do it manually. And time is critical when you deal with an infectious disease. So we're going to show you how digital twins can help companies get their employees back to work safely. And we're going to show you two of the big advantages of digital twins. One of them is the fact that they can provide almost real-time notifications. And the second aspect is that they help companies have a situational awareness of the entire population that they care about, and all of that for a very, very quick development cost, very low development cost. So for this demo, we are targeting a companies, a corporate environment, mostly because doing that for the public would be much more difficult because you have privacy concerns. You don't know if everybody's going to participate, or you don't necessarily have a unified tooling for all of this. But for a company, you have a much more limited population. You know your offices, the different clusters, and you understand their behavioral patterns and their interactions, whether they have meetings or conferences, and so it makes it a lot more practical. And also, simply, it's much easier for a company to adapt quickly and change their policies regarding safety procedures or how to organize, how to react to new information in real time. So the way we approached this was we designed a system that has two main components. One of them is an application, a mobile application that you can see some screenshots here. And the second part is the cloud-based digital twin service. So for the first part, the mobile app, that's how users will notify the service that they have established a new contact. So let's say here in this example, Lisa adds Emma as a contact after she met her. And so that's how you would create, you could keep track of contacts. So you can have like recurring meetings, you can have like team meetings that are automatically tracked by the system that way. That's also the app that you will use if you need to report a test result, a positive test result in this case. But that's also the app that you will use to get your notification. If somebody in your network has tested positive, you need to know and be quarantined as quickly as possible. So that's the interface that the users will use in that case. On the other side is the cloud service itself. That's what will track the employees, create all the notifications, and help the company obtain aggregated analytics in practically real time. So as you can see here, each employee is represented by a digital twin, and each digital twin maintains a list of contacts that the employee has had in the last 2 weeks, or this is configurable, but you could imagine that it's the last 2 weeks. And if an employee signals that they tested positive, then the digital twin will then go through the entire network of contacts within seconds and signal to the other twins that they need to take action. And the action in that case is what you've seen in previous demos. When you send the data back to the data source, that's how you can reach back to the mobile app in this case and create an alert that will let the user know that they should quarantine. And all of that can happen practically immediately as soon as somebody reports a positive test result. And all of that happens at the same time as the aggregate analysis, because each twin manages statistics that can be aggregated every few seconds. And that's what I'm showing here. So our cloud service takes all the data from all the different twins every few seconds. That's the map reduce that Bill was talking about earlier. And that will allow managers to quickly identify like clusters of cases, and very quickly react by either changing policies for a specific department if something like that stands out, or maybe cancel a conference if they see that there's a surge in a specific state. Or so as you can see here, those are two examples of widgets. We've talked about widgets earlier, where you could, for instance, show the positive cases organized by department or by state or by location, office location or something like that. So in order to show you that, what we did was we created a tool that allows us to simulate a company. We went for a mid-sized company of about 30,000 employees, spread into different department types. We have some retail, we have some engineers, and all across 8 different states. We have teams of varying sizes. And what this tool does, the load generator will basically create interactions between simulate interactions between the employees. So you can imagine like a team meeting, a recurring team meeting, or maybe a conference somewhere. So interactions with people either inside or outside of your organization. And while we model all of this, we also simulate infections in that population. And all of that, we could also control the actual time. So it runs faster than real time so that we can actually show something interesting in a demo context. And that's what I'm going to show you right now. So first, I'm going to show you here that we have the 30,000 instances, one for each employee. And I'm going to show you here the dashboard that I have created earlier. And as you can see, we already have one case in Florida that has been handled previously. So what we're going to do, I'm going to show you here the simulation tool. And as you can see here, we have a bunch of different parameters. One of them is here what defines how quickly the simulation goes. Here we have it set up to run 1 week of simulation in 7 minutes, so it's a minute per day. We have a bunch of parameters here that I'm not going to go into right now, but they control the types of interactions that I was mentioning earlier, like contacts inside or outside your team, conferences, and all of that. And what we're going to do here, we're going to imagine, oh, and I forgot about that section. That section is what controls the infection rate. So the 0.9 is the national average. You can play with that in order to create scenarios where you would have a surge in a specific state. What we're going to play with here is we're going to create a spike in Texas, and we're going to see how quickly, if I go back here, Texas is in red. So what happens now is that the digital twin will send notification to all their digital twins that were in the list of contacts. And at the same time, the system will aggregate, and here we go, we see the huge surge in Texas. And so the MapReduce took place in, what, 5 seconds, something like that, across all 30,000 employees. And we can see practically in real time a surge in Texas. And that's when a manager could potentially see that and maybe go and do a query to figure out here. I've already selected some of the fields that I care about, and you can run a query like Oleg showed earlier, and you will see very quickly who got infected. And for a manager, that means that they can contact them to make sure that they've acted on their notifications. So you have the notification that is sent individually to the employee, but the manager can also take action. We track a bunch of different other properties, and one of them is, for instance, the number of contacts that a person has had inside or outside their team recently, and that will give you an idea of how quickly you need to interact. In some cases, you could have like maybe 50 people, and you need to take real quick action in order to stop the spread of the virus within the company. So that's all I have for this demo. If you have any questions, let me know. Otherwise, I'll hand it back to Oleg.
Okay, thank you very much, Olivier. For our final section, we're going to let you build your own first real-time digital twin. And we'll start with Oleg giving you a description of the problem. And then if you guys can poll and you want us to wait before we show you the solutions, poll and tell us that, or do it in the form of a question, or chat. You could chat to everybody or something. But if we don't hear from anybody, we're going to go ahead and just start walking through the C# version and then the Java version. And then I'll do a 5-minute wrap up, and that will be it. So Oleg, it's all yours.
Okay, thanks, Bill. Let me open the slide which states the problem right here. So the goal here to build a digital twin which would be able to track the telemetry from a smart meter, and specifically from a gas sensor, and detect when the level of that gas exceeds the predefined threshold of 50 ppm for 15 minutes. And So the model is supposed to, again, code that. And a second condition when, and then after 15 minutes, you send alert, just set the alert flag within the model by itself. Let's assume somebody else will read it. Or you can send a message back to the device itself to indicate that command is supposed to shut down the pipe, incoming gas pipe. Second condition when the alert is set and you can send message back is when a single message comes in with the spike of the gas level more than 200 ppm. So those two conditions which triggers the alert, and as a bonus, you can again try to code sending that message, specific message, even alert message back to the data source, which is device. So that's the task, and we do have that model published to the GitHub, both C# and Java, and we can show how easy to solve that particular problem using our digital twin library, regardless of the language and the platform. So let me see the chat if somebody wants to start. And there's a question to us whether we can do the exercise in Java. Absolutely, yes, we can. And in fact, oh, where's the code? So Brandon, if you can send me a link so I can. Oh, so Brandon, send me a link to the chat to everybody. Send a link to the Java code through the chat.
So because I think we were planning on people writing the code, it's not posted on GitHub yet.
Okay, well, C# is posted, but sorry.
All right.
Okay, so then I'll make a presenter so we can have Brandon presenting that code. Just a second. Switch to.
And then we'll have that code up on GitHub later today.
Right.
Well, you'll get to see it now.
Okay, Brandon, is it for some reason it's not coming through? Make presenter.
Let me do it.
Yeah, for some reason. Oh, here it is. No, it doesn't go through. Bill, please help us. Okay, good. Oh, there's a question I didn't answer. Okay, good.
Brandon, you should be presenter. Yeah.
All right, so here it is. Let me just get situated. So I went ahead and I've also done the bonus assignment that Oleg assigned. So when we detect these limits, we'll call send a data source. And so before I even jump into the code itself, because we're familiar with the problem and because we're familiar with the mock environment and digital twins in general, I'll walk through what the test is gonna look like. So really quickly here, we're gonna create the mock environment builder. I'm just calling this natural gas meter. Created this instance of a message processor. I've created this natural gas sensor class, and I have the natural gas sensor message class. And then what this test is going to do is it's going to test that 15-minute time limit with the ppm being above 50. So I just chose to do 51. And it's going to calculate the current time and then time in 15 minutes just to make sure we hit an alert. So what we'll do is we'll go ahead and create one high PM message for now, serialize it out, send it to our natural gas meter, and then assert that we get the handled result back. And then we'll do the same thing, but have a high ppm message that's in 15 minutes. Then we serialize that out and send that to our digital twin. And then what we're going to do is again assert that the sending result's handled. And then now we'll get into something new, which is calling receive on the mock environment or mock endpoint. And what this will do is this will go to the natural gas meter model, pull all the messages for digital twin instance ID 23. And then we're just going to do some basic sanity checking here, making sure that it's not null, making sure that we're seeing size of 1. And then we'll just do a quick assert to make sure that what we see is warning dangerous air quality in the natural gas alert. So let's start by looking at the digital twin. So as defined in the slide, we have some constants that we have to define. So the maximum allowed reading at any, let me make it a little bigger. Give me a second.
That's great.
There we go. What we see is that the max reading is 50. The max reading allowed time limit is 15 minutes. And the max PPM reading spike is 200. So this is another unit test we could add to just make sure that if we see 200, we throw out an alert right away. Then we have some other dynamic state variables or here. So we have the last PPM reading, last PPM time, a flag to see if the limit has been exceeded, flag to see if the alarm has been sounded, limit start time, and the total number of events. Total number of events will be increased every single time we either see the spike or the max reading allowed. So natural gas alert is another very simple class. What this has is a message as well as a timestamp. And then we just return the alert message when we call get alert message. So two very simple properties. The natural gas sensor message is another really simple class. All we have is an integer for the PPM reading and a long, which represents the time when the reading was taken. And then we can jump into the message processor. So the message processor, once again, it's very simple. It takes as parameter the processing context. We're going to need this to send to data source. We need a natural gas sensor, which is our strongly typed implementation for the message processor. And then we have the list of messages that we'll receive from the service after they're sent to a digital twin instance. So we're going to loop through all our messages. First thing we'll do is we'll set our last reading based on the message reading time, and we'll set the last PPM time as the message timestamp. And then the checks here are fairly simple. What we're going to do is we're going to check the message for its reading and compare that against our constant. And if that's true, it's going to go into this loop. And note that this will handles plus. So this handles the max allowed reading plus the spike in the second conditional statements. So then we're going to check to see if the limit is exceeded. This limit is the amount of time between the readings. And then if that's not true, then we'll set the limit exceeded to true, set limit start time to message.get timestamp, and set and then increment the number of events. Moving to the one that sends the alert, we're going to check our time to see if we've if 15 minutes essentially has elapsed since we started measuring. And then we're also going to check to see if the last PPM reading was greater than the max spike, which is 200. And so if that's true, if either of those conditions are true, we're going to set natural gas sensor.set alarm sounded to true. And then I'm instantiating a JSON serialization framework here called JSON. And I create a natural gas alert. I'm just sending warning dangerous air quality with the current time. I serialize that out and then call processing context.send to data source to send it back to the device or the data source. So then if I go to our test, as I described earlier, make this a little bit bigger. What we're doing here is, again, very simply getting now and getting in 15 minutes. So that way we're making sure we hit that window. And then I'm going to check the received messages to make sure that we did send an alert back. So go ahead and run that. And we see that the test passed, so that's great. That means that one message was returned. So we'll go ahead and add a debug statement here, I think. That way we can look at our received message. Oops. Looks like we already had one. 8. So we see that inside received messages from the surface, should be down here. We have an alert message that says warning dangerous air quality with not the right timestamps. That's interesting. But the string is correct. So that is that sample. I think I will pass it back to Oleg now, unless there's any other audience questions.
Well, let me check the questions. Okay, there are some questions. And can the mock simulate send to source message? And we showed it can. Yes, that's
so that's the process.
That's the code.
Yeah, when you use the processing context, it's the exact same implementation for the full digital twin. So you use the full digital twin, and the processing context allows you to call a bunch of useful methods. One of them being send to source. So you can also do a log message. So if we wanted to log a mock log message, we can call log message as well. If we wanted to send to another digital twin, if we were using a hierarchical digital twin model, we could do that as well. So there's lots of options on the processing context.
So I want to add also to that answers. The mock environment represents the digital twin as well as the source. So when the digital twin sends message to the data source, it's within the same mock environment. You have access to the collection of those messages. So that's important to distinguish. So it contains basically both sides of the equations, if you want. Yes, you have a data source as your simulated device and the twin itself within the runtime, and you can have access both to the twin and to the data source simultaneously. Okay, the one more question, Brandon, to you. Can that digital twin receive a message from another digital twin? And it can.
Yep. So, and you can do all that through the mock environment. That would take some thinking to give an example of that right now.
But the main idea
but
here,
it is possible, yes.
When the message comes in to twin, it can came from another twin or from the data source, but it's still the same message you expect to receive. Yes.
Yep.
So you process in the same fashion.
Yeah. So if you were in the message processor and you wanted to send to another digital twin, you could use the processing context. You can call processing context send to digital twin.
Yes, and then you.
And then here you have. So let's say we have like a manager guest, something like that. Pass in an ID, or you could pass in some serialized message here. And note that when you send to a digital twin, you'll have to use, or you'll need to use a JSON serializable message. So for sending to a data source, you can use any serialized blob, but when you send to another digital twin, because digital twins all use JSON serialized messages, you'll want to make sure that this uses a JSON message.
Oh, great, thank you. There's one more question. Maybe I can just answer right away. The last one probably, Bill,
yeah, I'm answering that one.
But the one before, it says at the end of the talk, can you show where you use Ignite for this product? So the answer is no, we don't use Ignite. So this is all proprietary technology. We have own in-memory data grid. So we don't use Apache Ignite as a part of the product. That's the answer to that.
And I answered the other one.
Okay, good. And let me. Okay, I need to switch back to presenter role. Can I do myself or no?
No, I think I have to give it back to.
Okay, so maybe you can. Okay, show my screen. Okay. So let me open Visual Studio. So that project is uploaded to the GitHub. It's called Gas Meter Twin. So from the high level, if you hide the details, so you have a model class, which inherits from the abstract digital twin base class here. You have a message type, and you have a message processor type. In message processor, you need to override one method, and this is the for each loop where the logic exists in that particular example. When you send another message to the data source, I call it action command here, and you define the command description and maybe the code, which will indicate the device what to do. So now, as Brandon showed in Java, there are some constants defined in the section here, and there are some derived state variables we are going to use during the processing time, similar to what Java example showed. I'm not going that second time talking about each of them. And the logic in C# looks like that. It's one-page logic. So it's basically the same. You're going through the messages. If you exceeding the threshold, it triggers the processing within that condition, which again, take into consideration the spike and the duration of the interval you monitor. And at the end, you raise the flag, or you send the message to the data source in C#. It's just a few lines of code, the same as in Java. So you serialize to JSON the class here and extract the bytes and feed it to the send data source, and they get sent. So there's one unit test here defined, so you can play with that, or I can add later a couple more methods to indicate to check the spike and duration specifically. But that's the shortness of that code. So that's the goal. So it's a interesting problem, and there are many of them in the real life, and it's easy to solve those problems, to define the solution using our digital twin library, as you can see from those examples. That's the conclusion. So Bill, I can pass the presenter role to you if we don't have any specific questions regarding that task. Let me just look.
Okay, I think I can maybe just take control. We'll see.
Oh.
Yeah.
Okay, good.
Okay. So just to do a quick wrap up, can you see my screen?
Yes.
Okay, that's the wrong slide, but okay, good. Go to the right slide though. Okay, so we've been discussing this new software model for stream processing called real-time digital twins. And we got a question about, is this an actor model? And it's similar to an actor model. Actor models tend to be a lot more general. And I've had experience programming actor models in the past. They can be very complex to debug, to keep track of where all the messages go and all the state changes. What we tried to do is create a very simplified version of an actor model where we're really talking about pairwise relationships between physical devices and digital twin instances. And you can think of a digital twin instance as an actor with state and the ability to send and receive messages. But we've restricted that to make the development and use of them very straightforward. So for example, we have the ability to send messages directly back to the data source in this pairwise fashion. We also have the ability to have the execution environment connect to IoT hubs and other sources of messages. And of course, there's the integrated aggregate analytics. So it's really tailored for real-time stream processing. We had another question about how does this compare to Azure digital twins? And again, Azure digital twins are targeted towards describing hierarchies of things in the real world, as I was describing earlier, like floors and offices and light switches and tables and chairs and things. So you can very easily keep track of a very large collection of entities in a hierarchical manner and be able to manage, say, a complex office building and know what everything, what all the relationships are. We really went after, in some ways, a simpler problem, looking at pairwise relationships between data sources and our digital twins. But the goal is so that we can analyze telemetry and do so with context and be able to find strategic patterns and trends in real-time intelligent monitoring. So the goal is to complement the other services available in Azure and other platforms like AWS with a new streaming analytics platform that has these unique capabilities of deeper introspection on telemetry from data sources and integrated aggregate analytics. The net result is when applications have lots of entities, generally of the same type, like trucks in a fleet or people wearing healthcare devices or e-commerce shoppers, that you can very easily track their telemetry, understand what it's telling you, introspect about the state of the data source, react to this data source, and also see the patterns across all of those data sources. So it's one platform can't do all things. We targeted this to solve a relatively unsolved problem in streaming analytics and to leverage the power of in-memory data grids to do so. So just to go back to the slide, you can see that real-time digital twins give you a powerful new tool for doing this context-based introspection and responding, and they're very fast. They can respond in a few milliseconds, and they're scalable because we're hosting them on an in-memory data grid. As Oleg mentioned, just to go after that other question, we have our own in-memory data grid at ScaleOut Software. We are separate from Ignite. And so I don't want to confuse you to think this is an Ignite technology. Certainly this kind of software could be built on a platform like Ignite. However, our company has its own in-memory data grid that dates back to 2005 and has features in it that are really tailored for this particular API, in particular the using reactive extensions to deliver messages to objects within our grid, and other features such as integrated data parallel analytics, which we have tailored for this API set and for this application. It's strategic because of the aggregate analytics. Allows you to be able to see patterns and trends across a very large number of data sources and then query all of those digital twins to find out where problems are emerging and react to them strategically. The example I gave was of a forest fire emerging, and you have sensors on power poles, being able to find out where are the problems emerging, how serious are they, and how are they moving, so you can react to them. We also intended this to be very easy to use. That's another way you can compare it to other digital twin platforms. If you look at Azure Digital Twins, they have their own language for specifying these hierarchies and numerous other specialized APIs. We try to avoid that to the greatest extent possible to enable the most rapid adoption and the lowest possible learning curve. So we, as you saw today, we have very simple APIs in Java and C#, and you didn't see JavaScript, but we also have that. We're also working on a rules engine implementation for a digital twin, which we'll be releasing very soon. And the idea here is that you only have to learn a couple of base classes, like 3 or 4, and then you can be building a digital twin, letting the platform do most of the work for you for orchestrating their execution, delivering messages, and doing the aggregate analytics. So this streaming service and companion on-premises platform called ScaleOut Stream Server allow you to host large numbers of digital twins and visualize aggregate analytics and hopefully improve your situational awareness for applications that have large numbers of data sources. I really appreciate your attending today. One more slide. Thank you for joining us. And if we spoke about this earlier, but just to refresh you, our website is scaleoutsoftware.com. The documentation you can find under the support section of the site. That's the URL there. If you go to the support section and then click on documentation, you can find the user guide and the language-specific API documentation. The last thing is the GitHub repo, which we just stood up today for this talk, and has on it this slide deck and all of the demo code that you saw today. And if you have any questions, we certainly invite you to write to us. You can write to us at sales@scaleoutsoftware.com, or you saw our email addresses on our header slides. Feel free to write to any one of us with any questions or comments you might have, and we look forward to talking to you in the future. So thank you very much, and that concludes the webinar today.